Hey, welcome back, everyone. We are now on our third week topic, which is the theory of probability. So, what are the topic outlines for this topic? We have first, what is really the role of probability in statistics? What are events, sample spaces, and probability? The different types of events we have the compound event, complementary event, and a simple event. The different types of probability. We have conditional probability and unconditional probability. Different probability rules used for unions and intersections. And the last, some counting rules. Okay, so what is or what do you think is the role of probability in statistics? So without probability, there would be no statistics, right? Because statistics is founded on the study of probability. We need first to define and calculate or understand the characteristics of a certain outcome. I mean, what is the associated chance or probability of that event to occur in order to advance in statistics. And what I mean by that is in anything that you do, for example, you are predicting, you are guessing, or you are estimating, or just giving your judgment on something. We all use varying degrees of probability, okay? Because everything is subject to uncertainty. So that is why we need to have some level of confidence, and we use probability for that. Okay, so probability is very useful because it is the foundation in statistics. Okay, so events, sample spaces, and probability. What are these terms? First, we need to define what we mean by observation or measurement. Okay, so observation or measurement and experiment. Okay, so in other fields of sciences, experiment means a complicated process of conducting a research, for example, in order to obtain certain results. But experiment in statistics is wide. Okay, the meaning is broad. So experiment in statistics means any process or a method that produces or generates a data. Okay, any process or method that generates a data is what we call experiment in statistics. Okay, and that data is obtained by measurement or observation. Okay, remember observation, measurement, and you need to have an experiment in order to have data. So, for example, here we have two coins are tossed, and the up faces of both coins are recorded. The instruction is list all the simple events for this experiment, right? So we have an experiment which is very simple, composed only of tossing two coins. Okay, so the instruction is what are all these simple events? So I think this is a simple problem, and we can solve it right away. So let's say that the S, oh, it doesn't write one. Okay, all right. S uh, could be the outcomes could be first head and then head, head and then tail and so on. So the simple events are head, 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 tail, 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 and tail, head. The other rotation uses S and then semi or colon. So we could use equal or just colon. So that is all the simple event for this simple experiment. Okay. So when we say simple event, it means that that is the outcome that cannot be reduced any further. Okay. Means that is very specific. Okay. So you can only observe one and only one of these outcomes. The distinguishing feature of these outcomes is that these possibilities cannot be decomposed enough. Okay, the very basic possible outcomes to an experiment are called simple events. Okay? So the difference between the events versus simple event, this is irreducible, and this is a specific combination of simple events. Okay. So for example, you have a certain criteria and ask what are the event of observing or measuring at least one tail or at least one head. So that's combination of simple events now. Okay, so we have defined the event, we have defined the simple event. What about the sample spaces? The sample space is the collection of all the simple events. In other words, it is the universe. Okay. So, for example, if we draw a Venn diagram, which is the universe or the sample space of all the outcomes of the experiment of tossing a coin. Therefore, the simple events inside that universe or inside the sample space are the following. We have the HH, we have the HT, we have the TT, and we have the HH. So that's the visual representation of that sample space and the corresponding simple events. Okay, so let's continue. Let's have more examples here. Here we have table 3.1, experiments and their sample spaces. Experiment. Toss a coin and observe the up phase. Okay, remember, observe or measure are the same. So the sample spaces are you measure a head or you observe a head. The other one, you observe a tail or you measure a tail. So the sample space contains only two simple events because the outcome of tossing one coin is only two. Okay, so this sample space can be represented in set notation. It's called set notation. In some texts, they use equal sign and curly parentheses as a set containing two simple events, which are H and T. Okay, where H represents a simple event observe a head, and T represents a simple event observe a tail. Next, another experiment. Toss a die and observe the up phase. So we know that the die has six phases. Therefore, the sample space contains 1, 2, 3, 4, 5, and 6. So the set notation of that sample space is this. Next experiment. Toss two coins and observe the up phase on each. We just solved this experiment. And of course, you can observe HH, HT, and so on. And this is the sample space of that experiment, okay? And here in figure 3.1, we see these are the Venn diagrams for the three experiments from table 3.1. So in the first, we only have H and T for head and tail. For the second, rolling a die, we have 1, 2, up to 6. And of course, the last I just shown from the previous slide. Okay, so let's continue. So definition, let's have some definition. Uh, Probability. The probability of an event, simple or otherwise complex, is a number that measures the likelihood that the event will occur when the experiment is performed. The probability can be approximated by the proportion of times that the event is observed when the experiment is repeated a very large number of times. So, for example, a simple event E, we denote the probability of E as P parenthesis E, which creates the probability of event E. Okay. So what this means by this statement is when we say probability, okay, when we say probability, we do not mean that when you do a single experiment, the probability will always come out to be, for example, zero point 0.5 for tossing a coin. What we mean by that is that if you do it long enough, if you do it infinitely, okay, when you, if you do it uh, with infinite amount of time, the experimental value, okay, or the observed value of the probability will approach the theoretical value of that probability. And that is related to the law of large numbers. The law of large numbers. Okay. Of course, when you toss a coin, doesn't mean that, for example, when you toss 5 times or 10 times, it doesn't have to be 50-50. Okay? There will be numbers of 5, or 4, 6, and so on. But what we mean with that is that we believe that to be true because we are basing it on the law of large numbers. Right? So, for example, here in figure 3.2, this is an actual experiment. We have the sample size n on the x-axis and the proportion of heads on the y-axis. So at first, 250 samples, you can see that the number of heads does not stabilize at zero point 0.5, di ba? It, it prefers to have a value of around 0.45 or as low as close to zero point 0.4. But if you do it long enough, okay, if you have the luxury of time, you will see that the value, okay, the value approaches to the theoretical value, which is zero point 0.5. Okay, so the variance at this initial sample size is very large. Eventually, it gets reduced and reduced until the variance becomes zero. So this is what happens. The variance or the spread or the standard deviation gets reduced as you do it long enough. That is why we do sampling that has enough sample size in order to reduce variability. All right. Okay, so let's continue. First, what are the rules, the basic rules for assigning probabilities to simple events? Number one, first, let E sub 1, E sub 2, and E sub k be the simple events in a sample space. Remember, simple event means irreducible event. That is the ultimate outcome of a certain experiment. So first rule is that all simple event probabilities must lie between 0 and 1. Okay? It can never be greater than 1 and it can never be less than 0. So if it is equal to 1, it means 100% certain it will happen. If it is equal to 0, it means it is impossible to happen. Second rule, the sum of the probabilities of all the simple events in that sample space or in that universe must be equal to 1. Okay? Must be equal to 1. It cannot be greater than 1 or less than 1. It is always equal to 1. Okay? So, for example, we call the very first example, we have the sample space of HH, HT, TH, and tail. So the probability of HH, HT, and so on is equal to the total sample events, which is 4, to that number of that simple event. So this is one event, this is one simple event, one simple event, this is one simple event, and the total number is 4. So this is 1/4, 1/4, 1/4, and 1/4. And if you add all these probabilities for HH, HT, TH, and TT, you would always sum up to 1. Okay? So that is the meaning of rule number 2. All right, let's continue. An event is a specific collection of sample points or simple events. I just discussed this from the previous slides. And sample points are simple events that are in the sample space. Okay, so the H or the T for tossing one coin, that point is also called sample point. And the H is the simple event. Okay. So more examples. Example 3.2. Consider the experiment tossing two coins. I think the same example. If the coins are balanced, okay, then the correct probabilities associated with the simple events are as follows. Simple event. We have HH, HT, TH, and TT. Okay, we have 1/4, 1/4, 1/4, and 1/4. So we have a question here. First, define the following events. A is defined as observe exactly one head. So now this question is not anymore about simple event. This is just event because remember, simple event is irreducible, while event is a combination of simple events. So event A, observe exactly one head. So you can have H, T, you can have TH, right? That is at least observe exactly one head, right? So, because HH and TT does not belong to event A by its restriction. Second, event B is defined as observation of at least one head. So if this is event A, because at exactly one head, then observe at least one head, so you could have more than one head, and that includes this one. So this is event B. Okay. So figure 3.3 are the Venn diagrams visualizing the event A and B. So they are just the same to what I have drawn. Okay. All right. Let's continue. Okay. So let's have the SOP or just the standard operating procedure for calculating any probabilities of events problems. First, we have define the experiment, that is, describe the process used to make an observation and the type of observation that will be recorded. Okay, so this is very important. First, let's define the experiment. You have to define the experiment. How is the data produced? Or how is the data generated? By tossing a coin, by drawing a card, or by randomly sampling, whatever. Next, define the experiment. Next is define and list all simple events. Remember, simple events, not events, okay? We need first to have the general overview of the sample space, and that can be done by having an idea of what are the simple events. So again, define the simple events. Number 3, after you have defined the simple events, number 3 is to assign probabilities to those simple events. Okay, assign probabilities to those simple events. Right? That makes sense, right? After that, step 4, you have to determine the collection of simple events contained in the event of interest, of course, because most of the time the question is not about simple event, but about event or specific collection of event. So that's that fourth step, that specific collection. Determine the collection of the events. Okay, just the event. And the last, step five, some simple event probabilities to get the event probability. Four and five, I think they can be combined into one. Okay, sum the simple event probabilities to get the event probability that refers to the event in question in step four. Okay, so at least we reduce it to four steps. First, the detail of the experiment, and then the second, all the simple events should be defined. Fourth is what are the assigned probabilities to each simple event, and then answer the question of interest. And that is the collection of specific simple events. Okay, so let's have more example. Example 3.4. Let's read. A software engineer must select three program modules from among five that need to be checked for defective code. If unknown to the engineer, the modules vary in the effort required to debug them. In other words, the modules have different levels of difficulty. The question is, what is the probability that A, the engineer selects the two modules that require the least amount of effort? Letter B, the engineer selects the three modules that require the most effort. Okay, so let's apply the steps in solving probability events problem. First, let's define define the experiment. So first, let's say even E. So let's say M1 is for module 1, M2 is for module 2, and so on. And M1 is the least amount, the least difficult to solve or to debug, and M5 is the most difficult. So we have M1, M2, M3, M4, and M5 be the modules in increasing difficulty. Okay, so that's for the first step. The second step is assigning probabilities for each simple event. But first, of course, we can assign only if we have identified already what are the simple events. So out of five, the engineer has only to select three. So it could be 1, 2, 3, 1, 2, 5, and so on. So let's complete the list. So let's start with M1, M2, M3, right? And M1, M2, M4, and then M1, M2, M5, and then M1, M3, M4, M1, M3, M5, and then M1, M4, M5, then M2, M3, M4, M2, M3, M5, then M3, M2, sorry, M4, and then 5. The last is M3, M4, and M5. Okay. So these are all the simple events. So it's a combination of module. It's not specific arrangement, okay? One event is module 1, module 2, and module 3. Another event is module 1, module 2, and module 4. So overall, there are 10 simple events of selecting 3 modules out of 5. Next step is to assign the probabilities. So let's assume that each of these simple event is equally likely to occur. That means the chance of each event is 1 over 10 because the total number is 10. Okay, so 1 over 10. So I think we are now ready to answer letter A. The engineer selects the two modules that require the least amount of effort. So two modules, those are one and two, right? So what are the events here that contain one and two? Because selects the two modules, dapat the two modules that require the least amount of effort. So we have here M1, M2, and M3. It contains M1 and M2, the least amount, the least difficult. We have also M1, M2, and M4. So that's also another event or outcome that contains M1 and M2. And the last, of course, is M1, M2, and M5. So these are the only simple events that contain the two easiest module to debug. So I think we're now ready to solve for this. So let's define the probability of A as the probability of M1, M2, and M3. Let's just use that label. Plus the probability of M1, M2, and M4. Plus the probability of M1, M2, and M5. So the probability of M1, M2, and M3, because we assume that all has equal chance of occurring, therefore it's 110, it's the same, 110, and it's the same as 110. Therefore, the answer of this is 310. So there is a 30% chance that the engineer has a module that contains two of the easiest module to debug. We go now to letter B, question letter B. Question letter B is the engineer selects the three modules that require the most effort. And that module is 5, right? The engineer selects the three modules. Oh, the three modules that require the most effort. And of course, those modules are M3, M4, and M5. So, not lucky for the engineer, uh, ang module niya is M3, M4, and M5. And that event is this M3, M4, and M5. Therefore, the chance of that is 1 over 10. Let's write it down. The probability of event B is equals to the probability of selecting M3, M4, M5, and that is equals to 1 over 10. So there is a 10% chance of being unlucky. Okay? All right, so let's continue. We go now to compound events. What do we mean by compound events? First, let's define or describe the union and the intersection of two events, of two simple events. The union of two events, A and B, is the event that occurs if either A or B or both occur on a single performance of the experiment. We will denote the union of events A and B by the symbol A UB. Okay, so AUB for the union, and that is equivalent to A or B. A or B means sum, okay, or addition. Another definition, the intersection of two events, A and B, is the event that occurs if both A and B occur on a single performance of the experiment. We will write A intersection B for the intersection of events A and B, and this is the notation. And that is equivalent to having A and B, not addition, but the confluence or the combined characteristic of A and B. That is the meaning of that. Okay, so compound events means an event can often be viewed as a composition of two or more events. Such events are called compound events, and they can be formed in two ways. And of course, in two ways, it can be union or intersection. So graphically, uh, uh, this is what it looks like. So let's say we have event A and we have event B. Okay? And they are concerned for the intersection. So the intersection of that is this. Therefore, this is A intersection B. So notice the area is now smaller compared to A alone or B alone or both. So uh, the intersection, the result of that is the reduction of the area, or which means the reduction of the possibilities for the outcomes or the events. While union is just combination. So we have A, for example, and then we have B, for example. So if you just A and then union B, then you are referring to the area of this plus this. Okay? So that's a union. Although it doesn't look like there's a union, but mathematically it means A plus B. Okay? You consider the area or the all events of B and the all events or the area of A together. Okay? Because there is a special case of union where there is an overlap, and we will cover that in the next slide. Okay, so for example 3.5 uh, published a study on unintentional carbon monoxide poisoning of Colorado residents. The source of exposure was determined for 1,000 cases of carbon monoxide poisoning that occurred during a recent 6-year period. In addition, each case was classified as fatal or non-fatal. The proportion of the cases occurring in each of 10 source fatal categories is shown in table 2.3. 2. Now, define the following events, okay? We are interested in the events. Simple events or events. Event A. Event A is carbon monoxide poisoning case caused by fire alone. Event B, CO poisoning case is fatal. All right. So letter A, those are the events A and B. For the question letter A, describe the simple events for this experiment. Assign probabilities to these simple events. Right. So what's it mean to describe the simple events for this experiment? Uh-huh. So what it says here is that the simple events for this experiment are the different combination of exposure, source, and fatality status. That is right. There is a category for fatal, non-fatal, and sources of exposure. So the total number of events is 2 because there are 2 times 5. Sorry, 2 times 5 because there are two categories, fatal and non-fatal, and 5 because there are 5 sources of fire, sources of exposure. Fire related, auto exhaust, furnace, lines, other. So 2 times 5, there are 10. There are 10 simple events overall. Okay, so you can only fall in one of these 10 categories. Since the probability of an event is the likelihood that the event will occur in a long series of observations, the probability of each simple event can be approximated by the proportion of times the simple event occurs in the 1,000 cases. These proportions are listed in table 2.2. If you sum these 10 probabilities, you will find the sum to 1. Yeah, because that's the rule number 2. Okay, so that's for the description of the simple events. There are 10 simple events, and the sum is 1, and the total cases is 1,000. We can use this 1 if the question is interested, for example, how many fire-related accident under fatal or non-fatal by multiplying the probability or the proportion of the simple event to 1,000. Okay, so that's for the letter A. Letter B, describe A union B. So describe A union B means the union of A and B. A, we know that A is the poisoning case caused by fire. So this is A, fire related. This is event A, right? Event B, poisoning case is fatal. So this is event B. Okay. So the question letter B is describe the union of A and B, which means the combination of the simple events of A and B. Okay. So if we could calculate something, then all you have to do is add all of these: zero point 0.6 by 0.005, 0.02, 0.02, 0.07, and then 0.07, and then another 0.07. Okay, because that's the union. Even if there is an overlap or double counting, that depends if it is mutually exclusive or mutually not mutually exclusive. That will be discussed in the next slides. The question here is only to describe. Okay, so uh, yeah, so the union of A and B is the event that occurs if we observe a carbon monoxide poisoning case caused by fire exposure event A, or a case where fatality occurs event B, or both. Consequently, the simple events in the event A union B are those for which A occurs, B occurs, or both A and B occurs. Okay. So it could be fire fatal, fire non-fatal, and then auto exhaust fatal, furnace fatal, appliance motor fatal, and other fatal. So those are the AUB. So let's write this one. A, and that is fire fatal, fire fatal, hmm, fire fatal, fire non-fatal, and then um, auto exhaust fatal, auto exhaust fatal, furnace fatal, appliance, appliance fatal, then other uh, fatal. So that is the simple events under this event. Letter C. Letter C is the describe a intersection B. So we have already drawn event A and event B, but now the interest is the intersection. So the intersection is only this one. Okay, so that would be uh, fire under fatal. Okay, so that is the description of A intersection B. Now letter D. Calculate the probability of the union of A and B and the probability of the intersection of A and B. So for for P A U B, that means we have to add 0.05 plus 0.02 plus 0.02 plus 0.07. That's for B. That's for B. Plus for A is zero point zero 0.06 plus 0.07. So notice the 0.07 is counted twice. Okay? And the answer for that is wait, 0.05, 0.02, 0.02, 0.07, 0.06, 0.07. Yeah, that's right. So the total of this is equals to 0.245. Now for letter D, calculate the intersection. The intersection is A, U, B. That is only 0.07 because that's only the intersection of event A and event B. Okay, so welcome back. We now discuss the complementary events. What do we mean by complementary events? So the complement of an event A is the event that A does not occur. That is, the event consisting of all the simple events that are not in the event A. So as we can see in this figure, in figure 3.5, um, the event A has four sample points or four simple events. And when we say the complement of event A, we mean all that is not in A or all simple events that don't belong in sample space A. And take note that the sum of the event A and its complement will always be equal to 1 because the sum of event and its complement will always be 100% because it contains the whole universe or the sample space. So we have there the sum of the probabilities of complementary events equals 1. That is the probability of A plus the probability of complement of A equals 1. So let's have our example for complementary event. Okay, so example 3.7. Consider the experiment of tossing two fair coins. Calculate the probability of event A, which is a measurement or observation of having at least one head. So as we can see in figure 3.6, it is illustrated that the event A contains the outcome HH, TH, and HT because these simple events have at least one head, and that is the event A. So the complement of that is, of course, anything that is not the event A, meaning it has a zero head. And that is, of course, the outcome of tail, tail. But how do we solve this one? Okay, so the question is the probability of event A. Okay, so first let's apply the basic rules. First step, let's define. We have already defined the experiment and we have already identified the simple events. The next thing to do is to assign probabilities for each simple events. Okay, so first we have the probability of tail tail is equals to 1/4 because 1/4. Let's write it another way. The probability of AC is equal to the probability of TT, which is 1/4. So if we want to find out the event A, specifically the probability of event A occurring, then we need to solve for the complement of A, which is event A. So we know that the probability of A plus the probability of its complement will always equals to 1. And we have the information of this term. So PA plus 1/4 is equals to 1. Therefore, the probability of event A is equals to 1 minus 1/4, which is equals to 3/4. All right, so the probability of occurring or measuring at least one head is 75%. Okay, so let's continue. Okay, so conditional probability. Okay, so now let's discuss what is conditional probability. So far, the type of event probability that we have discussed is based on the idea of relative frequency of the occurrences of those events when the experiment is repeatedly done a very large number of times. However, there is a type of probability which is conditional. By the word conditional, it refers to the idea that there is a certain restriction. In other words, we are not interested anymore in the whole sample space, or we are not interested anymore in the universe. That is because we are given an information, or we have an updated data or information about something. That is why we can reduce our sample space from initially a bigger sample space to a relatively smaller sample space. To illustrate what I mean, let's have a look at figure 3.7. The event A there is the event of measuring or observing even, even outcome of a fair die. Okay? So this event A is the measurement of even. And of course, those sample events are 2, 4, and 6, while B is another event. So initially, a die has 6 simple events, right? So let me draw this sample space, and those are the 1, 2, 3, 4, 5, 6. So this is the bigger unrestrained or no condition sample space. So of course, we know that the if the probability of all sample space are the same, then the probability of 1, 2, 3, 4, 5, 6 is always going to be 1/6. Okay? But for instance, you were given an information that on a particular throw of the die, it was told, or you were told that the number or the outcome is equal or less than 3. Okay, so that's the event B, equal or less than 3. So those simple events are 1, 2, and 3. Okay, so if you were given an information, or you have updated your view or your understanding on a particular problem, then it only makes sense that the certainty would increase or the uncertainty would reduce. That's why we are no longer interested in the bigger original sample space. So what A intersection B would result to is of course the intersection of this and this. And the only element or single event that occurs in A and B is the event 2. So the outcome of this event is of course only the event 2. So what do we mean by conditional probability here? It means that the probability of getting even or 2 is not 1/6 anymore, but 1/3. It is because you have narrowed down your sample space from 1, 2, 3, 4, 5, 6. It becomes now 1, 2, and 3. Because again, you were given an updated information that that throw a die is equal or less than 3. And since you apply the initial restriction of even, then the number of even in that reduced sample space is just 1, and the number of simple events is 3. Therefore, the chance of having an even outcome is not 1/6 anymore, but 1/3. Okay? So that's conditional probability. So let me read the formal definition. To find the conditional probability that event A occurs, given that event B occurs, you have to divide the probability that both A and B occur by the probability that B occurs. And that is P, or uh, how it reads is the probability of A given that B occurs. Okay, that's how you read it. The probability of A given that B or event B occurs is equal to the probability of the intersection of event A and B divided by the probability of event B, given that the probability of event B is not equals to 0. Okay, so let's have our example on this one. Okay, so let's have this first example about conditional probability. Let's read. Consider the following problem in process control. Suppose you are interested in the probability that a manufactured product, example given a small mechanical part or any component, shipped to a buyer or you as a buyer conforms to the buyer's specifications. Lots containing a large number of parts must pass inspection before they are accepted for shipment. In manufacturing, they are called lots. It's a large collection of parts or components, and because they do not test every single part or component of a lot that gets produced every single day because they don't have much the time and it's very expensive. So what is happening is they pull or sample 5, 10 components or parts from that lot, and if the result is okay or good, then that lot is ready for shipment. Otherwise, it's no good. Okay, they can decide whether to ship it or not. The whole lot, okay, not the whole parts. So they sample only small number of parts for that lot. For example, if the mean product characteristic, let's say diameter, of a sample of parts selected from the lot falls within certain limits, the entire lot is accepted, even though there may be one or more individual parts that fall outside specifications. Okay, so yeah, it's possible to ship or to pass the lot without inspecting the whole of all the parts. Okay, so let I represent the event that a lot passes inspection, and let B, another event, which represents the event that an individual part in a lot conforms to the buyer's specifications. So notice, no, that event I refers to the event that a lot passes inspection. A lot, it's not the individual parts. But for event B refers to the simple event that the individual part is both B represent the individual part in a lot conforms to the buyer's specifications. Why is that so? It is because, right, when you order something from Shopee, Lazada, or TikTok, you as consumer or buyer, you have plenty of time and you can review it, you can study every single part or component of the product that you bought. So you have the luxury of time, but in industry, they don't have the luxury of time because they get produced tons of products every single day. That's why the description of the event I and B are just very fitting. Therefore, the intersection of I and B is the simple event that the individual part is both shipped to the buyer. This happens when the lot containing the part passes inspection and conforms to the specifications, while I, intersection of the complement of B, is the simple event that the individual part is shipped to the buyer but does not conform to specifications, etc. Okay? So assume that the probabilities associated with the four simple events are as shown below. Now, the problem is find the probability that an individual part conforms to the buyer's specifications, given that it is shipped to the buyer. Okay, so first let's analyze this simple event. First question, why is it called simple event? I is a simple event, B is a simple event, but the intersection and the union of two simple events creates another simple event. So remember that it is not a compound event, right? Or an event, because we just learned that event is a collection of simple events. So it is not simply a collection of event I and event B, because intersection and union is a logical operation. So it's not this collection or combination of events. So it produces a unique and new simple event. That is why it's called simple event, the intersection of I and B, for example. Second question. Second question. We know that I intersection B means that the lot passed the inspection from the industry, and that B means every part is okay or passed to the customer. I intersection complement of B means the lot passed inspection, but the customer or the buyer is not okay with it because he or she found one component or two that is defective. The question is, what is the significance or the meaning of the other two simple events? The intersection of the complement of I and B, and the intersection of the complement of I and the complement of B. Okay, you may pause the video if you want to answer by yourself. Okay. Okay, so the meaning of that probabilities, which is 0.15 and 0.03, is that even though the lot did not pass inspection, they still ship it away. Okay, and there is a chance that that lot is okay with the customer, or that lot is not okay with the customer. So of course they can ship it away because they're not testing individual all parts of that lot. It just happens sometimes due to chance that, for example, you get five parts or five components, and then it falls outside of or below your standards. And by chance, it can occur. Okay, but it doesn't mean that every parts of those lot is defective. Okay, and maybe not all part is very critical. So it has to be on the discretion of the inspector. Okay, so let's try to solve this problem. Again, let's read the question. Find the probability that an individual part conforms to the buyer's specifications given, okay, that's the keyword there. Given that it is shipped to the buyer. Okay. So let's start on this side. Solution. Okay. The probability of the intersection of I and B is given already, which is 0.80. That is 80%. Okay. And this probability is not conditional probability, but it is unconditional. Okay. And it is based on empirical data. It is based on observation. And unconditional probability is based on the wide or bigger sample space because you don't have any other data to update your uh, confidence about something. Okay, so this is the probability if the question is unconditional. Again, as I was saying, unconditional means your sample space is bigger because you don't have an updated information about the problem that you're dealing with. But for instance, you were given an information, and the information is this: given that it is shipped to the buyer, okay, meaning it passed inspection. Okay, so you can ignore I see here. So you can concentrate on this one, but you have to modify this equation because given that is a conditional probability. So the solution for that begins with writing the conditional probability, which is what is the probability that the individual part conforms, and that is B. B given that that it is shipped to the buyer. It means it passed inspection, and this is equal to Pi intersection P divided by Pi. Okay, so that's the equation because that's the interested question. Now, let's examine. Do we have the numerator value, which is the intersection probability of the intersection of I and B? Yes, that's on the table. It's 0.80. What about the probability of the I or the probability of the inspection? Do we have that value? Not yet, but we can find that value by adding these simple events. Because remember, P, A, and its complement is always equal to 1. Okay, but this is not simple event A, but still it's simple event. It's just a union or intersection of simple events. This equation still holds true. Okay, so we can rewrite P I U B plus P I U B complement is equals to 1. But this is not quite correct, but it has to be Pi because it is union. It is union, not simple events or intersection. Okay, so first let me illustrate this one, why this is true. Okay, assuming this is the I and this is the B. Okay, and which let's just write arbitrary boundary for the sample space S. We know that I B intersection is this, right? This is the I intersection B. But what about I intersection of complement B? Okay. So first let's examine or let's illustrate the same drawing, but the shading is different. This is I still, this is B still, and the B complement is everything that is not B. Okay, so the B complement is this, the whole area except for the B. So this is the B complement or complement of B. Now, what about the I intersection of the complement of B? So if this is the complement of B and this is the I here, therefore the intersection of these simple events is this right here. This is the intersection, or this is the intersection. Of course, this is the I, and this is the B. Okay, can you see, right? That the intersection of the I and the complement of B is this area. Now, if you add these two, the probability of this and the probability of this, you just transfer this one. Therefore, you get the I, the probability of I. So that's the denominator. So let's solve that one. Pi, we have 0.8 plus 0.02, and that is 0.80. No, it's tick. Oh, no, shucks. 0.80, 0.82. 0.80, oh, sorry about that. 0.82. Okay, so going back to the equation, and that is equals to 0.8 divided by 0.82. And the answer for that is Mm, wait. 0.976. 0.976. Okay. So that's the conditional. This is the conditional probability. So notice that the conditional probability is greater than the unconditional probability, 97.6%, and the other one is 0.8%. Why do you think the conditional probability is bigger or larger than the unconditional probability? I think one of the reasons is you have an increased knowledge of the system or the problem, and therefore your sample space is reduced compared to the uh, uh, less informed scenario. So you have increased your confidence over something. Okay, so